So this is our sieve experiment. Currently we have loaded it up with soil, which is sitting in the soup can from about here to here. It currently contains 420 milliliters of the sand material. The basin at the bottom is full of water, and this is our runoff spigot, which will take what flows through the material itself and put it into the measurable cup down here at the bottom. These rods are here for adjustment. We have the entire base sitting parallel and level with the height of the water at the top. We have a sponge down here at the bottom with some support that will help allow the water filtered through the sand to drain into the reserve pool or extra pool or whatever you want to call it. And this is sitting at our top. It is another beaker with holes drilled in the bottom and a sponge hot glued to the bottom of it itself. And that will sit up here at the top and act as our inflow to the experiment. So water will drain through the sponge into the soil, through the second sponge, into the reserve pool, down into the measurable cup at the bottom.
Stuart then poured 250 milliliters of water into the measuring cylinder to see if the water would fully soak through the sand and the sponges and get through to the other measuring cylinder.
We needed a constant head for the system, so we added straws to the side of the water for it to escape, so as to keep a constant pressure of the water to keep the results consistent and smooth. Was that a bit too...
I'll do a rough. I need more water. I need more seconds. I think it should be fine.
This is our pendulum experiment. The objectives of this experiment was to find the damping ratio for the pendulum. First we have to find the subharmonic motion of the pendulum, which can be achieved by the mass of the weight along with its displacement from the central position. The mass of the weight was on the weight itself. The length of the string we measured from the nail to the weight with a 30 centimeter rule. To ensure the accuracy of our pendulum, we built in cross support, so there's little to no movement within the base of the pendulum. The counterbalance at the back was to make sure that the pendulum does not fall forward or get affected by the pendulum's motion. When it came to recording the pendulum's motion, we did not bring the pendulum above 20 degrees, so this would stop sag within the string. We measured it for 10 swings once the pendulum had settled, so we could get the most accurate results possible. So when the pendulum is swinging, the centre of mass of the equipment changes as it swings sideways. We constructed the legs at the bottom, so when the centre of mass does change, it doesn't cause the apparatus to fall over. This is our wire experiment. The wire we were provided has been wound around 5 non-conductive screws to give 4 different lengths to measure from. Using the power supply, we put 1, 3 and 5 volts with 10, 30 and 50 milliamps of current through it. From this, we would measure the current flowing through the wire to make sure that it is consistent throughout the wire. This is so we could measure the voltage drops over the 4 lengths with consistency. We performed each of the tests 3 times to get ample accuracy. We made sure the wire was taut so as to keep an accurate length of the wire to measure so it doesn't affect the results. From this, then we could calculate the voltage drops over the current to get the resistance of the wire. Keeping the length of the wire consistent is crucial for the resistivity to be accurate.